All right, so welcome everybody to Hoon Academy Lesson 1, Introduction to Urbit and Hoon. Um, Let me know if you can see my screen. Um, Please drop a message in the chat if you can't see it. Um, okay, so far, you may have heard talk about things like planets, moons, and stars, and so forth. So what are these things exactly? Well, an Urbit ship, which encompasses all of these things, is a running instance of Urbit with a unique network identity like sample palnet or Zod or Bud or Tamlet Mondice. As a computer, an Urbit ship has state, which reduces the data stored as zeros and ones, as we learned in the previous lesson, and it has operations, which are formal rules for transforming the zeros and ones. So hopefully everybody now has gotten a planet, which is on the live network. And this is what is called a live ship. So live network identities are finite and valuable. So there are about 4,294,901,760 planets, 65,280 stars, and 256 galaxies in the Urbit network. So to be safe with these live identities, most people prefer to develop software on what are called fake ships. So this means that you can run an Urbit instance on your local machine that is not connected to the wider actual network. And this is the main development method that we will use in this class. So you may have noticed a question on homework 0 to set up a running instance of a fake ship on your local computer. And if you haven't done that yet, no worries at all, because we are going to run through it right now. And before I go through this process, I do want to note that Urbit runs on any Unix-based machine, which for most people is Mac or Linux. If you use Windows, you can still get Urbit to run, but you'll need to either dual boot Linux on your machine, or you can use something called Windows System for Linux, which lets you simulate Linux running inside the Windows environment. You can also use things like using a cloud instance of a Linux machine. There's a couple options here. So if you're using Windows, feel free to talk to me and we can figure something out. Okay, so first we will want to go to our terminal and make a new folder called Urbit, where we want our Urbit stuff to live. Yes, oh, if the audio cut out, I apologize. Just Windows subsystem for Linux is what lets you run Linux inside of Windows. The best option is going to be Linux or Mac, definitely. Okay, so we are going to want to make a folder called Urbit. Here, I've already made it. And let's go inside there. So cd urbit is a command to go inside the Urbit folder. Okay, next, we are going to navigate in our browser to this link. So let's open up our browser and go to this link right here. Scroll down to section 2. Choose which architecture you're on. So, for example, for Mac users, there's Intel Macs and Apple architecture Macs. You have to pick the right one that you're using. This is a Apple architecture Mac, so I'll click this, and then I'll copy the command here. And then you go back to your terminal, and then you paste that command, and then you run it. Okay, and what that will have done is downloaded the Urbit binary into your Urbit folder. Okay. Then once we have this binary downloaded, we can run it to create an instance of a fake ship. So to do so, we're going to use the following command, //urbit -f zod. So the -f means that it's fake, and the zod is the name that we're going to give to our fake ship. So I've already done this because it takes a few minutes, but if you're following along, you should do so now to get that Zod fake ship made. When you've already created a fake Zod, you run it with this command, //urbit Zod. And there we go. Now we've created an instance of an Urbit fake ship, and now we've booted into the Urbit environment. This is called the dojo. All right. Few questions in the chat. What's the better option out of the three for Windows users, dual boot subsystem or cloud? Maybe WSL, Windows Subsystem for Linux. That's what I've heard the most people use. But yeah, let's talk about it after class. So here we are in the Urbit dojo. So what can we do here? This is Urbit's command line environment where you can use commands to access and manipulate your Urbit computer. So the first thing we can do is we can run this command, which is called ls sen. This is similar to the ls command in Unix. And what this does is going to list all the files and folders that live at the current directory. Okay, so we're in the root of our Zod, and then we see all this stuff. There's all this stuff that lives here. However, now let's go to our file explorer on our earthly computer. So okay. So there's an analogy we're going to introduce here, which is called Earth and Mars. So Earth is our Unix computer where all of our regular stuff lives, and Mars is where all of your Urbit software and data lives. These two things aren't necessarily synced to each other by default, but we can make them sync to each other if we run certain commands. So if you want all of this data to show up on your Unix computer in the file system, you have to run this command, bar mount send base. So what's going on here? Bar mount is the command to take what's called a desk and make it show up on your Unix computer. Send base is the name of a desk. On Mars, Urbit is going to organize collections of code and data into things called desks, and every new ship has one desk by default, which is the base desk. That is the default desk that you're going to start off with. So I run bar mount base. In this case, it's already mounted, but if you didn't run it before, you wouldn't see these folders here. But now I can go into Zod, I can go in the base folder, and I can see all these files and folders here, which correspond exactly to all these files and folders here, which I can see on my in my dojo. Okay, so any questions on that?
I have a quick one, Jack. I think maybe I haven't created an Urbit file yet, but when I tried to run that command, I got a generator failure followed by a temporary failure.
Maybe can you stop by office hours after class?
Sure.
Yeah, that'll probably be the best way to debug. Okay. Any other questions? Okay. So this command is going to, that tells you how to make something that you did on Mars in Urbit appear on your Earth ship. Now suppose that you want to make a change on Earth. So you want to open up one of these files, maybe in your code editor, make some changes, and then you want that change to be reflected on your Urbit ship. So let's run through an example of how to do that. So what's called a generator is a snippet of code that you can run from the dojo. So I want to run this generator called hello world, and I do it with this syntax, this less hello world. But what happens if I press enter here? Okay. It seems that I have this previous version of the code. Uh, okay, so usually this wouldn't work, but what we're going to do now is show you how, if this didn't work, to make it work. So we're going to open up a new file in our file editor. This is just like a new piece of text. And then we're going to take this piece of code and save it inside of our fake Zod. So we're going to go to Zod, the base desk, and then the gen folder. And then we're going to save this as hello world.hoon. All right. So we've saved that. Then to make this appear on our Urbit, what you would do is run this command, bar commit send base. So this is saying the commit command, take those changes and push them to Mars, and do that for the desk, the base desk. We press enter, then we run this, and now this command is going to be running this code that is going on here. So in future lessons, we're going to use this series of actions to store and run code that you've written, that you're developing, and then you want it to run on your Urbit. Okay. So to close your Urbit, you can exit this environment at any time. You just do this bar exit command. And now you're back into your Unix terminal. This is no longer the dojo. Get back, you do /urbit zod. Boom, we're back in. And you can also do Control D to exit and then boot back in, just like that. So as you're learning to create software in Hoon, in Urbit, something that might happen occasionally is you might break your fake Zod. And to guard against this, we can create backups of the fake Zod in a very simple process. So if we just do this command, this is a command from Unix. What we're doing here is we're taking the Zod folder and we're copying it into a folder called Zod backup. And then now we have a folder called Zod backup. And if you ever need to restore this because it's broken, you just copy this into there, and then you're good to go. Okay, so let's get back into the dojo again. So the dojo is not just for poking around in Urbit and accessing files, and you can also run Hoon code directly in the dojo. This is what makes it very powerful. So the important thing to keep in mind, though, is that the dojo will only let you input syntactically valid Hoon code. If you try to type something invalid, it's going to make a noise just like that. That's telling you, no, you can't input that character because that would make incorrect Hoon code. Okay, so for example, something to know starting off with in Hoon is that when you represent numbers greater than 999, use a dot to separate every 3 decimal points instead of a comma. So if I try to type the number 1000, 1000, it's actually not letting me type that last zero because that wouldn't be valid Hoon code. But if I go back, put this dot here, 1.000, then we're all good. We try to press enter here. This isn't a well-formed number, so it's not letting us press enter and input that. In general, the dots go every 3 digits from left to right. So, sorry, from right to left. So 3 digits dot, 3 digits dot, 3 digits dot. And this is a correctly formed number. This represents the number 1,234,567,890. All right. Okay, so we're going to be using the dojo heavily throughout this course. And this will be your main coding environment that you start coding in. So it's good to get comfortable with. There's a few tips that I want to teach you guys that are going to be useful. So you can press up arrow. This goes back through all the commands, all the history of commands that you entered in here. And you can also press down arrow. And you can even clear the input by just continuing to press down arrow. That'll just give you a new blank line to work with. All right. So when you press enter, you see this bracket is facing outwards. And that means the last line was a complete Hoon expression, and this new line is a fresh start to a piece of Hoon code. So this means that your Hoon is starting here, and it's not connected to anything else that happened above. However, if it looks like this is the opposite. This inward facing bracket means that whatever you type here is going to be connected to what you just typed. So this is, you're in the middle of an incomplete Hoon expression, and you need to complete it. So we're still incomplete. And now we're back to a complete Hoon expression. So this is saying now we're starting from scratch with the code. What is the maximum integer size? I'm not actually sure. I think it's probably limited by Unix. I think it's effectively unbounded. There's no bound to the limit of an integer size, but obviously you could represent a number so large that it crashes the computer, like it exceeds the limits of the computer that is underneath. But in Urbit, theoretically, there's no maximum integer size. So, all right, continuing with our dojo tips. If you're stuck at something that looks like this and you want to clear it and start over, you can just press enter, and then now you're back to a new Hoon expression. Okay. If you ever created an infinite loop, if this is spinning forever and it doesn't seem to stop, you can always just do Control-C to interrupt and terminate a looping or a seemingly unfinished computation. Okay. If you have a line of text, you can do Control-A to go to the beginning, Control-E to go to the end. That's very useful. And finally, if you type something in the dojo and you want to get a list of how you could complete this expression, you can actually press tab. And this will tell you, so I did this bar C, and if I press tab, it's going to tell me I can do bar commit, bar CORS approve, bar code, bar cancel. So if you ever forget the name of a command or something, just press tab and that'll tell you all the things you can do. All right. Okay, so Philip says I pressed Control-Z and the Zod dojo is now gone. So that's because it kicked you out of the Urbit environment and you're back to your Unix environment. So then you'll need to run /urbit zod, and then you'll get back in there. Yep. Thank you, Yeb. All right. Moving on. So what exactly is your Urbit computer? We discussed last week that any piece of information is data represented as zeros and ones, and interpretation, a way to make those zeros and ones into something meaningful, right? So at the very base layer, your Urbit computer is indeed a sequence of zeros and ones. That's what it is on the hardware level. And if you go up to the highest level of interpretation, it's a computer, right? You can click on things, you can send messages and so forth, right? But in between those levels of abstraction, um, there's different layers that we can understand Urbit on. And if we just go up one layer from the zeros and ones, we can actually say that your Urbit is a big tree of numbers. It's a big tree containing numbers, and each number is a non-negative whole number, like 0, 1, 2, 3, 4, 5, up to infinity. Okay? So this binary tree structure is at the heart of the Urbit system. So it's important to understand it well. And that's what we're going to do in this section, okay? So 2 new words for you. And in Urbit, an atom is a single non-negative whole number. So these are examples of atoms: 0, 5, 1,566, 20 billion, and 1, so on and so forth. These are all atoms, just single numbers. Okay? A noun is the basic unit of what is in Urbit. Everything in Urbit is a noun. And a noun is defined recursively, meaning it refers to itself in its definition, but it's pretty straightforward, okay? So a noun is either just an atom, so just a number, or a cell of 2 nouns. So that means a noun can be a number, it can be a cell of 2 numbers, it can be a cell containing a cell of 2 numbers and a number, it can be a cell of 2 cells, and so on and so forth. Okay, I hope that makes sense. So a noun is a cell, it's either an atom or a cell whose each entry is either an atom or a cell. Okay.
So,
But I just,
so
yeah, go ahead.
a noun can also be an atom, but all atoms are nouns, but not all nouns are no, the other way around.
Yes, precisely. All atoms are nouns, but not all nouns are atoms. Yep. Okay. But I just mentioned binary trees. So where's the trees in here? Let's actually tease that out. So here's the same data structure represented on each side. On the left side, it's represented as a cell of cells, and on the right side, it's represented visually as a binary tree. Okay. So number 5 is also just the number 5. A cell of 5 and 2 is split into 2 branches with 5 on the left side and 2 on the right side. Okay. A cell of 5 and the cell of 927 is a tree where 5 is the left branch, and on the right branch, it splits into 2 and has 927 as the lower branches. And note, every time, see here, I'm taking this 2 and splitting it into a 927, right? So we're replacing a 2, a single number, with a cell, and that's exactly corresponds to taking a number here and replacing it with 2 branches, right? So here we're taking this 9 and replacing it with this 0, 1, right? And here we're taking this 5 replacing it with 8, 9. See that? That's the only change. And that's the change right there, right? Does this make sense to everyone?
Yes.
Okay, good. So if we're storing data in these sorts of structures, we need to be able to access parts of the tree to grab data from this, right? So what we can do is we can number the nodes of a tree like this. And this gives us addresses for every location in this tree. So for example, the address 1 grabs you this whole thing. The address 2 grabs you this subtree under this 2. The address 3 grabs you this subtree under this 3, and so on and so forth. As a concrete example, let's consider this noun, okay? This is a noun, it's a cell of cells containing numbers, and it exactly corresponds to this binary tree right here. So if we grab address 1, it's going to grab this whole thing. Grab address 2, it's going to grab this left subtree, which is 8, 9, 10, 11. Grab address 3, we're going to grab this right subtree, which is 12, 13, 14, 15. If we grab address 5, 1, 2, 3, 4, 5, it's going to be this 10, 11 right there. And to see this better, we can represent it like this. This is an equivalent representation. We're just putting the whole data structure inside the node that you'd get, that you'd grab to get that. So grabbing the address 1, this top, gets you the whole thing. Grabbing address 2 gets you this. And grabbing one of these addresses at the bottom just gets you that number. Okay. That makes sense to everyone. So this is just letting you visualize this a little better. Okay, so we can actually demonstrate this in the dojo. So to do this, first we'll need a way to store a piece of data in the dojo's memory with a name so that we can access it later. This is what we call pinning a face. So if we do this, this tis A1 and do 8, then I get this 1. Okay, this is V2. So these pieces of data are now stored in the local memory of this of your dojo. Okay. Something important to note is that this is not technically Hoon code. This is the distinction will be important later, but this is a dojo specific shortcut. It is not technically Hoon code. Okay, but let's use it for now. So let's do this in our dojos.
So you said, what was the term you used? KISS A1?
Yeah, pinning a face. Oh, so yes, we'll get into this a little later, but all these characters, all these symbols have single syllable names. So you can call it equals A1, but in Urbit lingo, you call this character a tis.
Got it.
Yep. Okay, so we're gonna do tis my tree, this data structure that we see here. Okay, so that stores this under the name my tree. Now we can grab subtrees of this. So if we do lust5.mytree, going to give you 10, 11. Why is that? That's because 1, 2, 3, 4, 5, 10, 11. You do lust10.mytree, give you the number 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So this dot means searching for something inside of this thing that comes after. And we can even use this dot notation repeatedly. So this is something interesting. This means go to my tree, get the thing at the 5 address, 1, 2, 3, 4, 5, which is 10, 11. Then inside that tree, get the thing at the 2 address, 0, 1, 2. That should be the number 11. That's the number. Why is that the number 10? Oh, sorry, not 0, 1, 2, 1, 2, 3. So 2 is right here. So thing at the 5 address, 1, 2, 3, 4, 5, is this. The thing at the 2 address, 1, 2, is this. Any questions on that? Okay. So suppose we don't want to necessarily express something as like pairs of things, but we want to say like, here's an object which contains 2 things.
Nodes begin at 0. Sorry, Jack. The nodes always begin at 1, not 0 then, right?
Yes, yes. 1 is the 1 represents the entire tree. Mm-hmm. Yep. Okay. So, suppose we want to say like, here's a thing which contains 3 things or 4 things, and so on and so forth. How would we represent that in Urbit? This is in general what's called a tuple. And we can represent tuples as binary trees underneath. So this is how we represent tuples in Urbit with a rightward branching tree structure. So we're just going to take the rightmost element of a pair and expand it into 2 things. And we're going to take this rightmost element, expand it into 2 things again, and so on and so forth. So if we enter these structures into the dojo, we'll see that the dojo just kind of formats them in a cleaner way. And it's going to say, yep, this is the triple of 1, 2, 3. And if we do 1, 2, 3, 4, same thing. So this is the quadruple containing 1, 2, 3, 4. And we can express these in tree form as well. So again, we're doing this rightwards branching. So 1, 2 is just this. 1, 2, 3 means we take this right element and expand it into a pair. 1, 2, 3, 4 means we take this right element, expand it into a pair, and so on and so forth. Does that make sense to everybody? So this is how we express, here's something that contains 5 things. Underneath, it's still like pairs of pairs, but it's just visually represented as 1, 2, 3, 4, 5, 5 things.
This is basically just an abstractive like representation of the nodes.
Mm-hmm. Yep. So underneath, it's just nodes. It's just binary trees, cells of cells, because that's like the primitive data structure of Urbit. But the you view this particular structure as a tuple of 5 things or a tuple of 4 things. Okay. So moving on. So above, we use these addresses to navigate within trees. And this is kind of like saying, go to 200 Main Street in Springfield, Illinois. It's kind of like it's kind of like addressing you to go to a particular location in the data, right? But when you're navigating in the real world, you can also use instructions like go right for 1 block, then go left for 3 blocks, then go right for another block, right? And you can navigate in a binary tree this way as well. And in Urbit, this is what's called LARC notation. So LARC notation uses the 4 characters, this minus and plus, and this left bracket and the right bracket. And that just lets you go left and right throughout a tree of data. So let's go back to our tree that we stored in the dojo. So if we do this minus or hep.myTree, that'll get you the left branch of that. And if you do this less or right of my tree, then you get the right branch of that. Yes, lark, L-A-R-K. I know you guys are hearing a lot of different things, but and if you do this minus left bracket dot my tree, that's saying go left and go left in my tree. And you can do go left and go right in my tree as well. And so on and so forth. Okay. So back to this analogy of navigating in the real world. Sometimes addresses are so notable that you don't need specific directions. For example, if I tell you go to the Eiffel Tower or go to the White House, those instructions clearly convey where you should be going, right? So in Urbit, we can do something similar. And what we can do are attach what are called faces to parts of our tree. So let's do this in our dojos, okay? So what we're doing here is my tree is the same data structure as before. However, we've attached these faces to let us refer to parts of it. So there's A, B, C, and a D, okay? So now we do this. And now you can do A dot my tree, and it gets us 10. You do B dot my tree. You can do C dot my tree, which gives you this. And you can get D inside C of my tree, which gets you this 12. Okay? D dot C dot my tree right here. And you can even use duplicate faces. So let's make my tree something different. Okay. Here, this tree has 4 different things which are called B. Okay, there's 4 different things called B here. So what's going to happen if you do B dot my tree? In some languages this would fail or be confused, but in Hoon it actually works because when you do this, Hoon is going to perform a depth first search and return the first match to B inside of my tree. So it's going to search and it's find 1. Okay. But you can also get any following matches. Any following matches. So this cat notation is saying skip the first match to B and get the second match. That gets you the 2. And you can use this twice to get the third match, and you can use this 3 times to get the 4th match. Okay.
Jack, isn't the numbering breadth first though? Why is this depth first?
Because depth first is saying you're gonna go to the left and go as far down as you can. So this data structure actually corresponds to this data structure right here. So you're going depth first, you're going here. That's the first B. If you want to skip this, then you're going to go right and then go left as far as you can. That's the second B. And then if you want to back out, then you go right and then you go left as far as you can.
Okay, gotcha.
Yep. So Isaac has a good question. So with this previous example of my tree, so this one, why does d.mytree fail? It's a bit of a like a particularity of Urbit, but basically it doesn't Urbit actually doesn't know, like it scans the structure and it doesn't know of anything that's called D. It only knows of D when it tells you to look inside C. So since this D is inside something named C, you have to say d.c.mytree to grab that. Okay. Okay. So we've given a brief overview of the way that data is stored on your Urbit. However, we haven't said anything about how the computer actually computes or performs operations on it. Okay. So to understand this, let's switch back to something that we learned in last lesson. So remember in last lesson, we learned about functional procedures, which consists of two parts, right? A functional procedure consists of the input and the function that you're going to run, right? And then we learn about the simple example of functions on binary tree. So can you guys tell me in this picture, which part is the data input, which part is the computational instruction? I mean, it's obviously labeled, but we want to separate this into two distinct things. The data input is this binary tree right here, and the set of computational operations is this chaining of write, subtree, and increment. All right. So let's rewrite this to make this distinction clearer. So we have this data, 1782, and we have a computation to be performed on it, which is take the right subtree of this and then increment it. Okay. And with this pair, we're going to perform a reduction process to get the result. So we put these together to get increment the right subtree of 1782. What we're going to do is we're going to reduce this inner part here. The right subtree of 1782 is 2. That gives us increment 2. Then we reduce this increment, perform that operation to get 3. Okay. Here's another example. So here we're going to get the left subtree of that, and then increment. So increment left subtree of the left subtree of this. Okay. So we reduce this to get increment left subtree of 17.8. So we reduce this in here. Then we reduce this left subtree to get increment of 17, and then we reduce that to 18. Okay. So let me just rename things now. I'm going to do exactly what I did before, but now I'm going to call the data input the subject, and I'm going to call the computation the formula. Okay. We're getting very close to something like NOC, which is the formal system that underlies Urbit. So a computation in NOC consists of two parts, which is the subject, the data input, and the formula, which are computational instructions. Both the subject and the formula are just binary trees of numbers or cells of cells, however you want to interpret it. So let's look at an example right here. Okay. So here our subject is this tree, which we just spent a long time looking at, 8, 9, 10, 11, 12, 13, 14, 15, right? And our formula is an instruction. It's just the cell of 0 and 2. What does that mean? So this means NOC instruction 0 is a computational instruction that says, take the number after the 0 and return what's at that address in the subject. So this is going to say, take this big tree and return what's that address 2 in it. And at address 2, it's this left subtree because 1, 2. So running NOC 0 on this gives us 8, 9, 10, 11. We can also interpret this in plain English, which is this 0, 2 is just saying grab subtree at address 2. We can also chain together computations in knock, okay? So consider this pair of subject and formula. And here we've written the formula in plain English, okay? So can anybody tell me what the result of this is going to be?
$51.
Yep, exactly. And how did you get that?
The address 2 is just the same as the left subtree.
Yep.
That's 50. And
Yep.
then add 1.
Yep, very nice, very nice. So you get the subtree at address 2, which is number 50, and you increment, right? We can do this in knock. So knock code 4 is a code that says compute whatever knock comes after me on the subject, then take that result and increment it, okay? So this is exactly the same as this, written in English, written in knock. So this is saying, we're going to take this pair, right? The subject is 589, and the formula is 402. We pull out this knock 4, which says increment the results of computing 58902. And what is 58902? Well, we just learned that knock code 0 says take the number after me, grab that address. So we're going to grab this address 50, which is, this number 50, which is at address 2. Then we're going to increment 50 to get 51. Okay.
So knock code 4 means increment?
Yes, it means increment the result of running whatever's after this 4. Do all knock instructions evaluate following knock instructions? Is knock 002 a valid knock instruction? So that's a good question. So the cell 02 is not a valid address, right? So we can try this. So there's room for running knock. So here let's set the subject, the cell 1, 2, 3, 4, and then let's say 0, 0, 2. So we're going to get a failure. So that's because 0, 2 is not a valid address. If you give it a valid address, then this works. But a cell is not a valid address, so you get a failure. So sometimes knock can fail if you give it something invalid, just as we saw failures in the binary tree example from last class. All right.
So the formula, which is 402, the 0 is the starting point of the node, and then it's 2 after that, or what?
Sorry, what do you mean by the starting point of the node?
Well, I'm not sure what the 0 stands for.
Yeah, so the 0. So let's go back here. Knock 0 is an instruction. So when you read this 02 as a formula, you're going to parse the 0 and you're going to say, okay, I know this is an instruction saying take whatever comes after this and get that address in the subject, in the data input. Okay.
So in this case, the subject is just 4, right?
No. So
Or
the
is
subject,
another instruction. Sorry.
yeah. So the subject is over here. It's over here. It's this thing that we're operating on. Yeah. So this means run the 02 and then get the result of that and then run the 4, which means increment.
How would you just increment on its own? Like,
yeah, so well, to increment something, you need to know what you're incrementing, right? So in knock, so we're not at Hoon yet, we're just in knock. But if you just wanted to increment the number 1, right? Well, maybe I could do something like this. That's going to fail because you're not telling the 4 what to increment. So if you want to increment this 1, you have to do the 4, and then you have to tell it, this is saying, grab the thing at address 1, which is the number 1, and then increment it. And that's going to give you 2. Okay.
So if you pass 4 an atom, will it just increment the atom?
No, because like if there's just a number here.
No, if you just, instead of a cell, just pass it an atom.
What do you mean by pass it an atom?
Left bracket 4,
Mm-hmm.
35 with no other bracket, and then the right close. Would that crash?
Like this?
Yeah.
So yes, this crashes
Okay.
because this is looking for something you pulled out. Right. I see what you mean. Like you kind of imagine you're substituting this 100 here, right? But it's actually the way 4 is defined. It's looking for a knock instruction. It's looking for something to run here rather than the data itself. A good question. Okay.
So it doesn't have modes. It just works the one way. That's really what I was trying to establish.
Okay. Gotcha.
Okay. Yeah.
Okay. So knock 3 says, similar to 4, says compute the formula after the 3 on the subject, and then return 0 if it's a cell and 1 if it's an atom. Okay. So how do we reduce this 5089 and this 302? We pull out this 3, it says return 0 if it's a cell and 1 if it's an atom on the result of computing 508902. What is 508902? Remember that knock 0 says go to this address and grab it. So we grab this 50, and now we're going to return 0 if 50 is a cell and 1 if it's an atom. 50 is just an atom, so we return 1. Okay. And we can test this out in the dojo with this rune. Three, 0, 2. And we get this 1. Okay. So one last knock code. So again, this is similar to before. Knock 5 is going to be followed by 2 formulas. Okay. Knock 5 is followed by 2 formulas. And it says compute both of those on the subject. And if the results are equal, return 0. And otherwise return 1. So this says compute 02 on the subject, then compute 06 on the subject. Then, if those are equal, return 0, otherwise return 1. Okay? So to reduce this, we're going to pull out the 5 and do these 2 computations. 02 on this gets the thing at address 2, that's 50. 06 on this gets, what's that address 6? 1, 2, 3, 4, 5, 6. It's going to be the number 8. It's going to be at the address 6. So is 50 equal to 8? No, it's not. So we get this 1. Okay. So the point of this section isn't to fully and completely understand knock, but we do want to get the flavor of it. And the reason being is knock is a very simple mechanical formal system, like formal systems we learned last class, right? It's based on binary trees, and it underlies Urbit. So the Hoon language is really just a layer over knock, and is very close to it. So by getting a feel for knock, we're going to be able to better understand Hoon, why it works the way it does. Okay. All right. So let's begin our dive into the Hoon language. And I apologize. I think we might be about 15-20 more minutes, so a little over the hour. But I appreciate you guys if that works for you. Okay. So let's get into our introduction to the Hoon language. So the first thing in Hoon we should learn is the idea of runes. And what is a rune? It's a combination of two symbols that let us specify different operations. And the first rune we should learn, the simplest possible rune, is the rune Cohort. Cohort. Okay, I'll type this rune in the chat for you guys. This Cohort takes two arguments and just puts them in a cell. That's it. So boom, we just made the cell of 1 and 2 with the Cohort rune. And the arguments to this rune don't need to be just atoms. They can also be cells themselves. So here we make a cell of the cell 1, 2, and the number 3. Yes, Cohort. And that's because this character is called Col and this character is called Hep. Yep. So something important to note here is Hoon's syntax. Spacing is very important. So Hoon differentiates between an ace, which is exactly 1 space, and a gap, which is 2 or more spaces. So if I try to run this previous code, and if I just put 1 space after that, it's not going to let me put 1 space, okay? I have to put 2 spaces to denote the children, different children of this room, okay? But I can also use more than 1 space, and that's totally fine. So I can do like this. This is exactly the same as this syntactically. And I can even press the Enter key in between lines. Remember, this is denoting that there's an unfinished piece of Hoon code. And that also works just the same. So pressing Enter is just the same as 2 or more spaces. Okay. So this rune is called Cohort, and we mentioned this a little bit. Hoon has a system by which every symbol we use is mapped to a single syllable name, and then runes are organized by their first symbol. So all the runes that start with Col are going to be about manipulating cells. So you don't have to learn these all right away, but as we go through the course, you're going to pick them up. And thus, let's just refer to them really easily by these simple names. Okay. So let's go back to the Cohort rune. And here, let's see something interesting. So the Cohort rune takes 2 arguments. But it seems like the second argument here to this Cohort is not a number or a cell, but it's actually another rune followed by 2 numbers. So in general, this is okay. Each of these children to the rune can be a noun, like just 1 or 2, or they can be complete Hoon expressions that reduce to nouns. So here, this Cohort 2, 3 reduces to the cell of 2, 3, and then that becomes a valid input for the second child of this outer Cohort. Okay, so this code right here, which creates 1, 2, 3, is exactly this. What's going on here? Okay. And we can also visualize this a different way. So what we did is we have a Cohort of a 1 and the second Cohort of a 2 and 3, and it parses as a tree like this. Right? So this is nested under the second argument of this outer Cohort. Okay. So let's consider a similar Hoon expression. This one right here. So what's going on here? It might be a little confusing to parse. So is this rune like argument to this? Like what runes do these numbers attach to, right? So this expression actually parses a tree in the following way. So this Kohlhep 1, 2 is the inner, is parsed, these are parsed together, like so. And that becomes the first argument to this outer Kohlhep. So it's a cell of 1, 2, and then a cell, and then 3. Hassan says, does it become a vector of 3 elements? A tuple of 3 elements, it's represented, it would be this. It would be this one. Good question, though. So a tuple of 3 elements will be like so. And you can see it printed in the dojo. Okay. So in general, when we're parsing these Hoon expressions, they're parsed from innermost to outermost. You read a rune. It says you need some number of children. You keep reading, and then at some point, these children are going to be completed. Then you can collapse this into a single expression, and you keep reading, right? So in this Hoon expression right here, we're going to take this Kohlhep 1, 2. We're going to read that, collapse it into the cell 1, 2. Then we're going to read this Kohlhep 3, 4, collapse it into the cell 3, 4. Then finally, this outer Kohlhep has just nouns underneath it, and you can collapse that as well into the final result. Okay. Okay. So now that we've gotten kind of the basics of Hoon syntax, let's learn a few runes that let us do the things that we just did in Knock inside the Hoon language, okay? So just like Knock, every Hoon computation consists of a pair of subject and formula, which are data in computation, right? The first Hoon rune we should learn is Tisgar, and that just takes something to set as a subject and something to evaluate against the subject as a formula. So let's try some examples, okay? Here, we're saying Tisgar, set this tree as a subject. This is the tree that we studied before. And then this dot just says return the whole subject. Okay, so this is the second argument. This is the first argument. And then we're going to get this whole tree back, right? We can address as before. Get the +2 address, get the +3 address, and so on and so forth. The next rune we should learn is Tisgal, and it's exactly the same as Tisgar, except the arguments are reversed, right? So if you do Tisgal +3, that's the formula, that's the code we want to run, and the data input is this tree. Then we're going to get this subtree of it, okay? Next rune we're going to learn is very simple. It's called .lus. It takes a single child, which must be an atom, and just increments it by 1, okay? So for example, we can do Tisgar 5, and then dot. That just says return the subject. Just going to return this 5. However, we can also do set the number 5 as a subject, then increment the thing at the subject. And that gives you the number 6. Okay. This piece of code says set the cell 3132 as a subject, get the thing at the 3 address, and then increment it. That gives you 33. And this .lus is the equivalent of the not code 4 that we learned about, okay? However, we can just add 1 to 5 in a much simpler way. And you can just do this in the dojo, .lus 5. That gives you 6. So what was going on here? Here I was doing this with this Tisgar, setting something as a subject. But in this piece of code, I'm just incrementing this 5. And it seems like there's no subject formula pair going on here, right? Like I said that every piece of Hoon code has a subject and a formula, but this is just seems to be just a formula. So what's going on here? Turns out that every expression that you type into the dojo is wrapped in a tisgar, giving it a default dojo subject to evaluate against. So if you just type something in here, it's actually wrapped in an invisible tisgar, which gives you this default dojo subject to work with. Okay. So when I do dotless 5, it's actually an expression like this. If I just do dotless 5, it actually has a hidden tisgar, which is giving you a subject to work with, but you just don't see it. Okay. So this constraint is preserved, that there's always a subject and always a form. Why is right. So let's go back to this. Yes, so Neil has a good question. So this expression says, give me a subject, give me a formula, give me a subject and something to compute on it, right? Takes 2 children. This is the first child. The first child of this is just the number 5. And then the second child is the instructions. So you want to, these are grouped together as the instructions, and this is the data input. So this is saying, get the subject and then increment it. Does that make sense? This is not a complete Hoon expression. Yep. Okay. Okay. So the .what rune corresponds to not code 3 that we learned. And it's going to return 0 if a Hoon reduces to a cell and 1 if it reduces to an atom. So for example, this piece of code set 589 as a subject, and we're asking, is a thing in address 2 a cell or an atom? We're gonna get a no. This is going to say this no is actually a 0, sorry, 1 underneath. It's going to say no, this is not a cell, this is an atom. This 50 right here. Finally, .tis, the equivalent of not code 5 that we learned above, takes 2 pieces of Hoon and returns 0 if they're equal and 1 if they're not equal. Okay. So here we're doing what we did in the knock above, which is take the cell 589 and ask whether the thing in address 2 and the thing in address 6 are equal. And no, they're not equal. All right. So why is this returning send.n instead of a 0 or 1? It turns out that these send.n and send.y are actually numbers underneath. And we can even test this with our .tis rune that we just learned. So send.n is actually equal to 1, and send.y is actually equal to 0. So these are just like layers over this number that we're learning. Okay. So what exactly is going on here? So knock, the machine language of Urbit, only knows about numbers. However, for practical computing purposes, you need much more than just whole numbers, right? You need negative numbers, you need floating point numbers like decimal numbers and text strings and so on, right? So what Hoon can do is it can take these underlying numbers and interpret them in different ways. And this is what's called an aura. So, for example, we just learned that send.y is actually just the number 0 underneath, but interpreted as an aura. Okay. And in fact, Urbit's famous sig symbol is actually just an aura over the number 0. And the galaxy Zod is actually just the number 0 underneath as well. Okay. So we can see this by doing something called casting. We can take this data and cast it to a different interpretation underneath. For example, here's the syntax to cast something to the empty aura, which is just no interpretation whatsoever. So if we cast Zod to the empty aura, you get 0 out of it. And same thing if you cast this yes, you get a 0 there. Floating point numbers. If you cast this big number to a pat rs, this is a floating point, you actually get this 3.1415. And these fractional numbers are going to start with this dot to indicate that it's fractional and it's not a whole number. Okay. This pat t aura is for text strings. So if we take this big number, oops, and cast it to a pat t aura with this syntax, you get the text hello. So the text hello is just this number underneath, interpreted a certain way. And same thing for ship names. So if we take this big number, cast it to a pat p, which is the name of an Urbit identity, you're going to get sample palnet. All right. So there's a lot more different auras than what we can cover here, but this is just an example to give you the flavor. So all these different data types in Hoon are really just big numbers underneath, just interpreted with different lenses, right? Okay, so that brings us to the end of today's lesson. Thank you everybody for being here. To summarize, we learned up how to set up our fake ship and learned how to sync files between Earth and Mars, right? We studied how to address and manipulate binary trees, and we learned the basics of Nock, which is Urbit's machine code, its underlying fundamental language. From there, we began our study of Hoon with some ways that Hoon corresponds to Nock. And then finally, we learned about auras, which is Hoon's way of interpreting these natural numbers that underlie Nock as different types of data, as not just numbers, but letters or ship names or fractions and so forth. All right. So if you made it here, congratulations on finally starting to get a handle on the Hoon language. And I will be holding office hours in the Hacker House right after class at this link. I hope to see some of you there. All right.
Thank you.
Yep. Thank you guys.
Thanks a lot, Jack.
Yep.
Thanks.